Okay, we're recording. Great. So I think we're going to get started, and I am happy to today present to you Professor Silvia Toonen, who was my former colleague and friend at Amsterdam University, where she's actually moving back to soon. So Silvia did her PhD in Nijmegen in the Netherlands, and later she moved to Leiden on a postdoc. And after that, she won the Winnie Fellowship as a postdoctoral fellow in the University of Amsterdam. After that, she got a faculty job in Birmingham University, where Silvia currently is, working on gravitational wave part, I think it is. And then now, soon she's going to move back to Amsterdam University as a faculty position, and she's hiring PhD students. So if you know any interesting and good student, I'm sure Silvia would be happy that they would apply.
Yeah.
So Silvia is an expert in dynamics and stellar evolution, I would say. She knows very much about multiple stellar systems and multiple systems. And she has, the past few years, I think, had a focus on gravitational wave progenitors, which I think is a quite interesting direction, since most of the time we focus so much on just binary evolution, but actually most of the massive stars have triple companions, as probably Silvia is going to say, so I will not steal it. And anyway, okay, I will shut up and yeah, take it away, Silvia.
Thank you, Ilva. That was a really nice introduction. And I want to thank Ilva and Tony for the invitation to tell you a bit about the work that we're doing here in Birmingham and soon in Amsterdam. So it's fresh off the press. I'm going to start there in January. So, well, good times coming. So what I decided to do with my talk is I wanted to start at the end. Let's see if I can go to the next slide. There we go. So what I wanted to do is to start with a very, very short and a very, very basic summary of what I'm trying to show you today. And that is that these kind of systems where we have two stars that are in an orbit around each other, they're abundant. And the stars in these systems, they evolve, they grow in radius, they interact with each other, and every now and then they give rise to these bright transients that we love and observe. Now, besides these sources, we also have these sources. So this is where we have three stars in an orbit around one another. Now, we know that that third star can have a very strong impact on the evolution of that inner binary. But what I want to know is, how does it affect that inner binary? And when does it affect that inner binary? And for how many triples is that third star really important? So the thing is that triple evolution for stars has only been studied in a few very specific cases. And so an overall picture of stellar triple evolution is missing. So that is something that my group is trying to change. Now, why do I care so much about these binaries and the triples? Well, that's because they can give rise to mergers of stars, to collisions between stars, gravitational wave sources. And when we get these mergers of compact objects, we get the formation of heavy elements. I think they're also interesting for supernovae. So for example, Supernova Type 1As, which likely come from the merger of two stars. But even your Supernova Type 2s, those stars that explode, they are likely affected by previous binary interactions. They're also interesting, in my opinion, in the context of planet formation, because the architecture of these systems, what kind of orbits and how often do we find them in binaries and how often do we find them in triples, says something about star formation. And I think that has valuable clues for us to understand, the formation of life. And the last thing I want to mention is that a lot of accreting sources that we see might come from these massive systems. And as Silvia said, they are often fine in triples. So I'm wondering how that changes the demographics of these sources as well. Now, I think if there's one thing that transient astronomy has shown us in the last decade, it's that there's a large variety of different transients. And sometimes it's called the zoo of transients, which is a name I really like. So for example, for supernova type 1a again, we have the stereotypical type 1a, but we also have subtypes like 91Bgs, 91Ts, O2ESs, calcium-rich transients. There's all of these different types of transients. And for many of them, we don't understand what their origins are. So for some of them, we're still arguing which stars are even involved to get that transient. And for other sources like gravitational wave sources, we kind of know which kind of stars are involved and what their masses are, but we're wondering how can we get those stars so close to each other that they actually end up merging. Now, this field of transient astronomy is, for me, very exciting because there's such a tremendous amount of progress coming from the observational side in the next few years. So this example that I really like is that currently with ZTF, we're finding of the order of a few supernovae every night on average. Now with the Vera Rubin Observatory, with the LSST survey, this is going to go up, or at least it's the expectation, to 1,000 supernovae per night, right? This is going to go up in the next 3 years with 3 orders of magnitude. Okay, I shouldn't exaggerate, 2.5 orders of magnitude. But so that's amazing, right? And that will give us, of course, a lot better statistics on our transient population, but it also does something for the peculiar transients. So many of the transients that are very odd and very peculiar right now, they are not going to be peculiar anymore in just a few years. And I think that really means that us as theoreticians need to step up and, need to focus on those, peculiar transients as well. So I want you to keep that in mind when I talk about these triples, which also might sound a little bit peculiar. But as our observational samples are growing that much, I think it's time that we start focusing on these systems as well. So usually that brings me to the slide that gives you an overview of what I want to do today. But I have 2 more slides that I want to show. And the reason why I implemented these 2 slides is because I know that many of you work on galaxy evolution or on stellar streams, or usually focus on single stars. And so what I wanted to show is that even when you observe single stars, these binary interactions or triple interactions can be of relevance to you as well. So here is a project that we did in the last couple of years, and it focuses on the solar neighborhood. And this is a sample that contains pretty much all the white dwarfs in the solar neighborhood within 20 parsec. So the completeness level of this sample is 95 to 99%, and that's insane, right? That's a very high completeness level. It's as good as complete. Now, what is so nice about white dwarfs, that is that we can use them as a tool to measure stellar ages. Because if you measure the temperature of the white dwarf, then you have a pretty good idea of how long that white dwarf has been cooling in time. And if you measure the mass of the white dwarf, then we can do a pretty good estimate for how long it would take a star, to evolve from the main sequence to all the giant phases and eventually form that white dwarf. So if you only have the mass and the temperature of a white dwarf, you have a pretty cheap way of measuring ages. So that's awesome for galactic archaeology. Now, there's one thing that this sample shows that is a bit peculiar. That is that if you look at that sample, about a quarter of all the systems are binaries and multiples, roughly a quarter. Now, if you look at the progenitor of your average white dwarf, so that's, say, 2 solar mass star, then the binary fraction of those stars is about 50%. So it's twice as high. So what happened to all of these binaries? And this is often called the missing white dwarf binary problem. Now, one of the things that has been discussed is that maybe these white dwarfs are all hiding, in the glare of your very bright companion star. But I'm actually saying maybe there's a different reason. And the reason that I'm interested in are the stellar mergers. So what we did in these projects here is we did modeling of large populations of binary stars. And in particular here, try to do a theoretical make a theoretical model for that 20 parsec sample. So based on everything that we know about binary evolution and star formation, history of the solar neighborhood, what do we expect for the white dwarfs in that sample, and how well does that matches with our theoretical expectations? It's one of the best tests that we could do for our methods. So what we found is that a large fraction of all the white dwarfs that are currently single actually come from a merger between two stars. So 10 to 30% of all the single white dwarfs. And that rate of mergers, that actually comes from all different types of mergers. So it can be two white dwarfs that merge, but also a giant with the main sequence stars, all different types of mergers. That merger rate also matches with the empirical merger rates of related events. Granted, the uncertainties in the empirical rates, is kind of substantial as well, but within that, it's consistent with our simulations. So this is something that we should keep in mind when we do galactic archaeology, that even if a star is single right now, it doesn't mean that it always was single. So that brings me to my outline slide, as I showed before. So what I want to do today is talk about triples. And I want to start with giving you a bit of a feeling of how triples evolve differently than binaries. Then I want to make that link between triples and transients. And in the end, I want to talk a bit about Supernova Type 1a. And I want to present or introduce a new channel to form Supernova Type 1a's that's actually considering binaries and not triples. So not everything will be about triples. Okay, so let's start at the top. So the first thing that I want to show is that these triples are common. So what you see here is the binary fraction on your y-axis as a function of spectral type. And as we saw before, the binary fraction for solar type stars is about 50%. For triples, it's about 10 to 15%. This is all observationally for young systems, right? So 10 to 15%, it's not super high, but it roughly means that 1 in 4, 1 in 5 binaries has a third companion. That starts to add up, right? That starts becoming significant numbers. Now, what happens if we go to more massive stars, and Ilva already alluded to this. If we go to more massive stars, we know the binary fraction goes up. The binary fraction for O and B type stars might be as high as 70%, maybe even 100%. Now, what do triples do? They seem to follow the same trend. So we don't have a very good measurement, empirical measurement of the triple fraction. So this number that I'm showing here is a lower limit based on the work of Yuxana, because it doesn't correct for observational selection effects. And I have to mention the work from Max Mo that tried to compensate for these selection effects. And he finds that the fraction of systems with 3 or more stars would go up to about 80%. So making actually triples and quadruples the common way for massive stars to be in, more common than binaries. And this is why I think they're so excited for gravitational wave sources, as Ilva said in the introduction. So the kind of triples that I'm talking about, they look like this. So we have 2 stars in that inner binary that rotate around each other, and then a third star that's in an orbit around the center of mass of that inner binary. So I'm going to talk about isolated triples and triples where we can talk about 2 orbits, an inner and an outer orbit. So you're going to hear me, use those terms as inner eccentricity and outer eccentricity a lot. So it turns out that, and these kind of systems, they can be stable for very long time scales. So time scales longer than the Hubble time scale, which means that they can also survive for so long. So again, meaning that they have potential to be abundant, as we saw in the observations. They are abundant. So it turns out that if you want to simulate or understand the evolution of these triples, we need 3 ingredients. The first ingredient that we need, of course, is 3-body dynamics. So you might remember from your undergraduate course that we don't have a general solution to the 3-body problem. So instead, what we have is approximations that are valid in certain parts of parameter space. And I really have to give so much credit to this field because there's been a tremendous amount of progress in the last 15 years in this field. So we have a much better understanding of specific behavior that are possible for certain combinations of masses and orbital architectures. Most of those studies, however, they approximate the stars by a point particle, which makes absolute sense, right? Like if you want to understand 3-body dynamics, that's where you start, and it's a pretty good approximation of a star. But also at some point, you can understand that that assumption isn't valid anymore. Stars are not point particles. So if we want to do this consistently, we need 2 more ingredients. We need stellar evolution. We need to take into account that these stars lose mass in their stellar winds. And we need to take into account that these stars grow in radius when they become giants. And the other ingredient is dissipation. And Tony knows all about this, right? We need to take into account tides if the systems are compact. And we need to take into account that their orbits can change if there's gravitational wave emission, or if gravitational wave emission is efficient. Now, there's been a handful of, I should say this differently. There's many papers that focus on 3-body dynamics that ignore these latter 2 processes. And there's been also a number of studies that focused on these latter 2 processes, but ignored the 3-body dynamics. And so far, there's only been like a handful of papers that looked at this combination of these 3. Now, for exoplanets, this combination has already been, recognized to be important in the evolution of the systems. And the same holds for binaries near supermassive black holes, which also kind of form a triple. But we now also need to do it for stellar triples. So with that in mind, I developed a code called TRES, in which we really combine these 3 processes simultaneously. And today what I want to do is show you some of the results that we have made with this code so far. Before I go to the results, I want to show you one more thing, and that is I want to give you a bit of a feeling about 3-body dynamics. Like, what does that bring to these sources? So just a few slides on that. So as I said before, the kind of systems that I look at, they have this inner and this outer orbit. And the way that I model the 3-body dynamics is by approximating this system as 2 wires. And the density of the wire is inversely proportional to the orbital velocity. Now, the 3-body dynamics in this picture, they manifest itself as an interaction between those 2 orbits. So it's a torque between the 2 orbits. It's a perturbation on the orbits. What that means in reality is that I have a set of differential equations that we solve numerically. And again, I wanted to give you a little bit of that feeling and of what these equations will bring about. And I can do that by either taking you through every term, or I do it in a different way. So in order to do that, I brought a tool, and Ilva knows what's coming. And for that, I have to stop sharing my screen for a second. So I'm just gonna ask Ilva if you guys can see me now. Does it work? Can you see me?
Yes, we
yes. Perfect. Okay, so I brought a tool, and this is really a highly advanced technological tool, right? So keep that in mind. So the tool looks like this. So this orange orbit, that's going to be our inner orbit. That's, the inner orbit of the triple. And then in blue here, I have the outer orbit. So let's aim this so that you guys can see it. Yes, okay. Orange, inner orbit, blue, outer orbit. Of course, this thing is completely not to scale because then I couldn't have it in my hand. This white little line here, you're also not seeing, that doesn't exist. That's just for me so that the thing doesn't fall out of my hand. So what happens in this three-body dynamics is that we get different cycles. The stereotypical effect, the lowest order effect of the three-body dynamics are called Kozai-Lidov cycles. What happens in those cycles is that the inner orbit changes its inclination, while the relative inclination changes, right? So it goes up and down. At the same time as this inclination changes, also the eccentricity changes. So we're more eccentric, less eccentric, more eccentric, less eccentric. I'm going to do that at a slightly different angle, just so that you can see it. So more eccentric, less eccentric. So we undergo these cycles. Now let's go back to sharing my screen. There we go. Share full screen. Yeah, there we go. Ilva, is it showing? Perfect, thanks. Yeah, so to show this in a more quantitative way than with my amazing technological tool, I'm showing here an example. So this is just for one triple. And in red, you see what would have happened if that inner binary would just be isolated. So the eccentricity wouldn't change, the inclination wouldn't change. Now, if I put that third star around it, we all of a sudden get these cycles. And you can see that the eccentricity, in this case, becomes as high as 0.9. So that's very high, and it can even become higher. The time scale of these events, of these cycles, really depends on the periods. So there's a number of parameters, but the rough picture to keep in mind is that the time scale of these Kozai-Lidov cycles is roughly the ratio of the periods times the outer period. So if that outer period is very long, then also these time scales are very long. Now, as I said before, these Kozai-Lidov cycles are just the lowest order approximation of the three-body dynamics. If we go to higher order terms, we get more extreme eccentricities, and we even can get inclination variations that are so strong that the inner binary does a flip and it changes from prograde to retrograde. I want to advertise really quick this Jupyter notebook that a student of mine made. And the idea here is that when you're observing and you find a triple and you want to know what kind of dynamics is important for this triple, you can just plug it in this notebook and it makes this picture, puts it in, and you immediately know, okay, where we have this standard Kozai-Lidov cycles, or we have these higher order terms, or maybe if your system falls in this black space, part of parameter space, that's where the system is dynamically unstable. So dynamically unstable systems, I'll talk about more later, but they tend to dissolve very quickly. So you would be very lucky if you find the system there. You can find this link, of course, in our latest paper. So why do I care so much about these eccentricity cycles? Well, I want to show you that in this image here. So again, I'm going to take a binary and then put a third star around it. So in this case, blue is the binary, and this is the evolution of time if it wouldn't have that third companion. On the y-axis, you see the size of the orbit, and pretty much nothing happens to it. It just becomes a little bit wider because of the stellar wind mass losses. But there's no mass transfer, no interaction. Now, if I put a third star around it, we see something that's completely different. So what you see here, if we zoom in on this spot, is that we see those strong Kozai-Lidov cycles. And at some point, the eccentricity is so large that one of the stars fills its Roche lobe and it starts the mass transfer phase. In this case, an unstable phase of mass transfer, which means a common envelope evolution for the experts in the room. And that means that the orbit here is going to shrink very strongly. A little bit later, that happens again. We get another mass transfer phase and eventually a merger. Now this system is really, really cool. And the reason is that this merger here is between two carbon-oxygen white dwarfs, two massive carbon-oxygen white dwarfs. So this merger is expected to give rise to a supernova type 1a. So I take this binary that didn't even interact and I turn it into something that gives rise to a supernova type 1a. So I think that's a very cool thing that a triple can do. Now, you know, the feedback that I would give myself here in this story is you can always come up with one system that does something interesting, right? You can always come up with some kind of weird evolution. So the question that I have is, how often does this really happen in the full population? So what we did is we simulated a population of triples, started here with low and intermediate mass primaries, and tried to see what kind of evolution do they undergo. Now, in this pie chart, I'm showing you we find 5 different main channels, and the predominant thing is that there's mass transfer in the inner binary. That happens for about 65 to 75% of all the triples in my population. Now that's a nice number by itself, but it only means something if I compare it to whatever happens in binaries. So for the same type of binaries, the same mass range, we would expect mass transfer to happen in only 30 to 40% of all the triples. So or all the systems. So even though, so with that third star around it, mass transfer is about 2 to 3 times more likely to happen. So even though triples are a little bit less common, if they interact more often, again, it makes them even more important systems to study the evolution of. There's a range, I'll skip this. There's a range of other scenarios that can happen. I'll talk a little bit later about the dynamically unstable systems. I'm gonna go through some of them. So here on the bottom, you see the purple ones. That's where there's no interaction. And it's really cool, but with Gaia, we found the first of such systems. So we found the first triple white dwarf. The first triple white dwarf in white orbits. There's one other triple white dwarf, but it has more compact orbits. But this system here definitely proves that these triples can really survive until the compact object phase. So that's a nice confirmation of our modeling. The other thing that I want to mention is the green part of the pie chart. And that's a scenario where you have a third star that's donating mass to an inner binary. So I think this is really cool. It happens in about 1% of my triples. And about 1% of triples, that's the first thing that happens. And then, you know, it's also possible that the inner binary already underwent some mass transfer phases and then the tertiary filter rush slope. So recently with Nathan Lee, we tried to estimate how often that happens. So for example, about 5 to 10% of all double white dwarfs should have a third star that transfers mass to it. The cool thing about this scenario is that you would get accretion onto these stars, or even maybe form a circumbinary disk around the inner binary from which it can accrete. And in that case, for example, you can form twin blue stragglers. That is bringing me towards the second part of my talk. And this is when I slowly want to start talking about transients. So when I reach this part of my talk, I always feel a bit like that. It's like I've been trying to paint this elegant picture of triple evolution and, you know, all the beautiful dynamics that takes place there. But the best thing is destroying it all. So that's what I'm going to do. We're going to destroy the triples. And the best way that I can think of destroying a triple is by taking a system like you see on the left, so these systems I've been talking about so far, and having these systems evolve into something that looks like this. So I hope you can see the movie. I guess you can. Waiting for I think Ilva was distracted by the movie. That's okay. So these kind of interactions that you see in this clip, they are the ones that you expect in stellar clusters, right? So here we started with a binary and we shot a star at it, and you get this beautiful, almost chaotic behavior. So in this case, we started with, a binary that had the 2 red stars, and we ended up with a binary that had one of the blue stars and one of the red stars. So we had an exchange of the stars. So that is one thing that is possible when my triples start to try to make this transition. When they go from this left side to right side, we might disrupt the triple, or during these interactions, we might also get very close passages. So we might strip some of the mass of a star. We can end up with very eccentric binaries. And we can also end up every now and then with collisions between stars. So that I will show now, actually. So that happened in about 2 to 5% of all the triples in my population. They became dynamically unstable. The ones that I focus on so far are the ones that become dynamically unstable because of their own internal evolution, just because of their stellar winds. So that shows that we really need to take into account 3-body dynamics and stellar evolution simultaneously. Let me check the time to see how much time I have. I will just go very quickly through this and saying that when we have wind mass loss, if it's an adiabatic effect on the orbit would widen. Now the amount of widening, you can see in this equation here, is directly proportional to how much mass is lost. Now the trick here with these triples is that if we start losing mass from the inner binary, then that inner binary relatively loses more mass than the triple as a whole. So that inner orbit is expanding more than the outer orbit. So this inner orbit is slowly approaching the outer orbit, and that's when systems become dynamically unstable. So we find a rate of about a few per kilo year in the Milky Way. And about 10% of them are expected to lead to collisions between stars. So that actually means that this would be the dominant way of getting collisions in the field. And normally when we think about collisions, it's about stellar clusters. It's about that movie that I showed before. But with triples, we can also do it just in the field. Now, another way in which a triple can become dynamically unstable and make that transition to a dynamically unstable system. I should mention, by the way, that can I go back? Yeah. I should mention, by the way, that I'm interested in the systems that make the complete transition from the left to the right, but also systems that just move further towards these systems that evolve on shorter dynamical timescales. So they don't completely have to become dynamically unstable. We just want them to move in this direction so that their dynamical timescales become shorter and more things happen. So one of the ways in which that can happen is due to a supernova. That brings me to massive stars, and that brings me to gravitational wave sources. So let me show you the channel that I have in mind here. So this channel consists of originally 3 main sequence stars, 3 massive main sequence stars. What we did then is we simulated the evolution of this triple, the stellar evolution, the interaction, the effect of stellar wind mass loss, the supernova kicks. We made different assumptions for the initial orbits, etc., etc. Then we focus on those systems that survive until the moment where we have 3 black holes. At this point, some of these systems have made that transition to a different dynamical regime, to that regime where Kozai-Lidov cycles are stronger. This induces very strong eccentricities in that inner binary to the point that eventually it can merge. Now, how that happens, how that works in reality, or how that works most of the time, is that we get a very eccentric binary. And when the stars are very close to each other, gravitational wave emission and GR precession become very strong. It becomes so strong that it swamps the three-body dynamics. And therefore, from that point on, that inner binary is kinematically decoupled from the outer star. So we end up with this compact inner binary that can just merge because of gravitational wave emission by itself, but driven there and put there because of that high eccentricity made by the outer star. So when we try to estimate how many of these sources we expected, we found a rate of about 1 per year per gigaparsec cubed. And I have to say that this is at solar metallicity, and of course for LIGO sources, we know that lower metallicities gives higher rates. So at lower metallicities, the rate goes up by a factor of a few. And that makes this channel to give rise to something that's maybe consistent with the lower limit of LIGO, which would mean that, you know, in the next observing run, there's potential that one of the sources that we observed there actually would come from this channel. Now, that also means that there's other channels, right, that give rise to gravitational wave sources. And Ilva already mentioned isolated binary evolution is one of the channels that many people consider and are studying. And also stellar clusters can form gravitational wave sources or can lead to gravitational wave mergers because of the dynamical interactions in the cluster. So my triples here, I always struggle a little bit to figure out in which category we should put them, because they are isolated evolution, but they include dynamics as well. So I tend to call these cluster evolution and this isolated binary evolution, just because otherwise I don't know where the stellar triples should go. Now, the most important point here, of course, is can we differentiate between these different channels? So turns out we can if we have a look at the eccentricity. So here you see a histogram of the eccentricities of our sources the moment that the source enters the LIGO band. And in black you see our triples, and in blue and red you see the binaries and the cluster evolution. I should mention that the simulations here that about the cluster evolution, they didn't take into account secular evolution for the triples. If you do that, because of course there's also triples and clusters, if you do that, then they also find a tail to larger eccentricities. And there's one other scenario in which you can also get eccentricities in the cluster sources, which is if you take into account 2.5 p.m. terms in the dynamical interactions. Saying that, for the majority of sources, our triples have a significantly different eccentricity than the other two main channels. So that's awesome, right? This is a way of differentiating them. Also should mention that an eccentricity of 10 to the minus 3 is still pretty much 0 for LIGO. So LIGO is not going to be able to differentiate based on eccentricity, but with LISA we would be able to do that, because when the source is still in the LISA band, the orbit is still wider, so the eccentricities are still lighter, and it might even still undergo Kozai-Lidov cycles. So that's one potential way in which we could recognize these triples. I am gonna go to my last part of the talk before Ilva kicks me off, and that is, that's bringing us to a different type of transients. So this trick, this channel, I've been focusing on black holes, but can't we do the same with other stars, right? Can we do the same with neutron stars or with white dwarfs? Now with white dwarfs here, I wanna push the limit a little bit further, and that is, I don't want to just have two white dwarfs merge, I want to have them collide. So I want very extreme eccentricity so that we get a direct collision between the white dwarfs. Now why am I interested in this? Because of Supernova Type 1a. They are one of the brightest explosions in the universe. You know, what can I say about Supernova Type 1a? need very little introduction, I think, in an astrophysics institute. I would mention that one of the problems with type 1As is that we still don't know what their origin is. So the two classical ways that we have tried to investigate their origin is by these accreting white dwarf systems called single degenerate systems, or mergers between two white dwarfs. There's also many other channels that are sometimes mixes of these two channels or additions to these two channels. I don't have time to go through all of them, but the important thing here is that none of these channels are completely capable in explaining all of the observables of supernova type 1a. The problem with type 1a's is almost that we have so many observations here, have so many strong constraints, that it makes it really tough for the theory to explain them. So for example, your single degenerate channel, the accreting white dwarfs, they have a tough time explaining sources at late times, so at long delay times, and also the rates. Then on the other hand, the double white dwarf mergers, they do quite well in the rates. But as it turns out from detailed simulations of their mergers, very often they do not actually lead to an explosion. They do not lead to a supernova type 1a, but instead it would collapse to a neutron star. So this is the problem with the current models. And at the same time, it's important because we're using the type 1a's, of course, to measure distances. So this uncertainty on the origin of type 1a's gives us a systematic error in using them as distance indicators. So yes, I'm going to focus on collisions of triples. And the nice thing about this channel is that the collision itself is what starts the ignition. So the ignition mechanism is very well understood. And that is not the case for the other scenarios where the ignition mechanism always gives rise to free parameters. Now, so what I did is I simulated the evolution of all of these sources and tried to estimate their rates on full binary and triple evolution calculations. So the observed rate of supernova type 1a is often measured in a kind of strange unit. What this means is if you have a group of stars in the sky with a total mass of 10,000 solar masses, how many type 1a's occur in a Hubble time? Observationally, that's about 10. Theoretically, what we expect for these accreting white dwarf systems is at best a rate of about 1. I'm saying at best here because this is for quite optimistic assumptions for how efficient a white dwarf can grow in mass. For the double white dwarfs, it looks a little bit better. It's not super comfortably reaching the observed range, but at least same order of magnitude-ish. Now, what do triples do? Can we solve this? No. I think this triple channel has, at least according to my simulations, the triple channel is at least a factor of 1,000 lower. So I think triples will not help here, just because supernova type 1a are so common that we need that whatever forms them needs to be something that very frequently occurs in stars or that involves, very typical stars. So therefore, I want to propose a new scenario that involves binaries. So this is work that is done together with Hagai Peretz and Joseph Senati. Joseph is a graduating PhD student, so most of the simulations of the merger models are really credited to him. So this channel involves a merger of two white dwarfs, where one white dwarf is a hybrid white dwarf. Now, what do I mean with a hybrid white dwarf? I mean a white dwarf that has a large CO core and a very thick helium envelope. So most of the time, when we think about white dwarfs, they pretty much either consist of helium or either consist of pretty much CO with a very thin atmosphere around it. Now, these hybrid white dwarfs, they can have a helium layer that's as thick as 1/10 of a solar mass, which here would almost be 1/4 of its total mass. these stars are actually super, super common. The way to make them is in a binary. Just one phase of mass transfer, you strip off the hydrogen envelope, and we end up with a star that's a helium star. It's one of those stars that Ilva is studying. A little bit lower mass though. These have a mass of about 0.5, 0.5, 0.6. These stars are so low mass that they don't evolve, well, that they continue burning helium in the center, but they don't become fully fledged giants, so they don't have strong wind mass losses. And because they don't become so big, they also don't interact with their companion much anymore, which means that nothing much happens to this star, and that CO core will just be there, and the helium that's on top of that CO core will just stay. So the next thing we did, or that Joseph did, is simulated the merger between these two stars. So this is two dynamical simulations, 2D simulations, and this is like the typical starting point of those simulations. And that's that we assume the hybrid white dwarf is completely disrupted, forms an accretion disk around your CO, and here you see a slice through that. So this is your central CO and the white dwarf, and this is your, slice through the accretion disk. In the next panels, you see how slowly mass is being transferred to the carbon-oxygen white dwarf. It's building up, and at some point, the density and the temperature in that layer become large enough that it detonates. That sends a shock wave into the core of the CO white dwarf, and then sets off a second detonation, which leads to the explosion of the white dwarf. Now, the reason why we get this explosion in this merger model, while the standard double white dwarf merger models did not, the reason is that we have a lot of helium. And it's been known for a while that helium really helps in getting that first detonation, right? Helium just burns at lower temperatures than CO. So what this channel brings is just a very natural way of having that helium in your system. Now, this next thing that Joseph did is fed his simulations into Supernovae and tried to estimate the spectrum. Just keeping an eye on time. Yes, I'm wrapping up in 3 minutes. So the spectrum that he got from this is shown here in blue at 2 different timestamps. And in red is the observed spectrum of the best observed supernova type 1a. And this is not a fit, right? This is just an overlay of 2 of our models. And I hope you agree with me that this is reproducing the main features of the spectrum already quite well. The next thing to look at is the light curve. So here in symbols, you see a number of observed supernova type 1a. And the dotted lines are, again, just two of our models. And they're showing that overall luminosity, we're reproducing the classical supernova type 1a's, and also the time scale of these events is fairly well, or seems to fit really well. Now, this luminosity and time scale are very useful quantities when looking at transients. That's also why this plot is so useful. It's a Tauenberger diagram, where you see the luminosity on the y-axis and the time scale of the event on the x-axis. So the very fast decliners on the right and the very slow evolving systems, transients, on the left. Now, the only other models so far that have been able to give rise that succeeded in getting an explosion and also give rise to also make a spectrum are these mergers of very massive carbon-oxygen white dwarfs. And they give rise to very luminous supernova type 1a. The arrow here represents the difference in the viewing angle. Now, our sources lie here. So they do not reproduce the very luminous sources, but they're actually reproducing those sources that the other channels do not. And besides that, they're also showing these transients where we have these other categories of supernova type 1a's or supernovae type 1a likes. So I want to focus just on these two. So these are in the yellow region of calcium-rich transients. So here in blue, you see the stereotypical example of a calcium-rich transient. And in red, again, one of our models And again, I hope you agree with me that these really reproduce the observations fairly well. Now, what is different in this system? Here, it's not the hybrid white dwarf that's being disrupted, but it's the other one. So it's the hybrid white dwarf that's secreting a lot of mass. So there's a very thick layer of helium on that white dwarf that explodes, gives rise to a lot of helium burning products, and therefore we get the calcium. Overall, this scenario leads to a very uniform picture where very luminous supernova type 1a come from these massive carbon-oxygen white dwarf mergers, and a variety of other transients can be explained with these different mergers that involve a hybrid white dwarf. I should say here that the points and the symbols represents my models for binary evolution. So this is where you would expect, this is how you would how we think that reality populates this diagram of masses. The last thing that I want to show is the rates, because as I said before, the supernova type 1a rate is very high, and from empirical constraints from Danny Maus's group show that about 15% of all double white dwarf mergers should lead to a supernova type 1a. That's how many we need to have, how common it is. Now, our scenario here, it's a little bit hard to estimate the type 1a rate because we just have a handful of systems, and we need to understand better which systems exactly lead to an ignition and which not. But overall, we can say is that about 25 to 30% of all double white dwarf mergers involve a hybrid. And they are in those areas of phase space where we think they're roughly massive enough to give rise to a supernova type 1a. So far, this is the only channel that very comfortably reaches the rates of the supernova, of the observed supernova type 1a. Now that was really the last little bit that I wanted to show you today. I'll just recap really quickly that I think it's such a bright time coming for these stellar transients, stellar interactions as well, because there's so much observations coming for the transients as well as for stellar populations that really will give a lot to this, to my field, but we're trying to understand these interactions. So I hope to have sparked a little bit of interest in triples for you guys. They are abundant, they are out there, and we will see them. We now have tools to simulate their evolution in a consistent way. And I'm very excited to see, what triples can do more, because our evolution or our research so far has been very limited. So that's something really that I'm looking forward to see change in the next few years. Lastly, just want to put up there our channels for gravitational wave sources where I think triples are important. Stellar collisions in the field. Unfortunately, I think they're not so important for supernova type 1a. I think that's important to show as well, right? To be fair. And lastly, our channel for supernova type 1a that involves the hybrid white dwarfs. And with that, I want to give the floor back to Ilva.
Thank you very much, Silvia, for a very nice talk. I enjoyed that a lot. I want to ask the audience for questions, and I think that we already have 2 in the chat. So I wanted to ask Lynn if you would like to ask your question by voice, and you can keep your hand up in the Zoom window if you would like to ask a question, and I will take you one by one.
Hi, this is Lynn Hillenbrand over at Caltech. This was a question that related to your introductory material, and I was basically asking for a better description or a more complete description of the problem of the binary issue for white dwarfs, and whether that was also true at the low mass and where we're finding identifying more of these systems. And I just don't know the statistics as to whether there's also a problem there or it's only in the FGK types that are, sorry, earlier type stars that you mentioned.
You mean the binary fractions?
Correct.
Yeah. What is your question exactly?
we can move on because your talk really wasn't about this, but it was more, you were saying that there was a deficit of identified multiplicity in white dwarfs as companions to, I guess it was AFG type stars. Yeah. And I was wondering whether that was also true lower down in the mass function where the white dwarf.
Oh, okay. Yeah, so the reason for me to show the AF, the solar type stars and a little above is because those would give rise to the white dwarfs. So, we start with the progenitor or AFK stars, then evolve and then end up with the white dwarf. So if the binary fraction changes, something must have changed, during that evolution. But if we go to lower mass stars, then yeah, you're right? I showed this other plot of the binary fraction, and we know it goes down if you go to lower mass stars. However, then the orbits are different, so the interactions are different, and they don't form white dwarfs in a Hubble time. So
no, I wasn't talking about the M dwarf would be the secondary, right? Instead of having a white dwarf primary with an AFG secondary.
Oh, okay. So
the secondary would be the M dwarf, and those are much more abundant because they're much easier to find. Sorry, not more abundant. They're more deeply cataloged because they're easier to find and identify. But again, this wasn't really the topic of your talk, so we can move on to Wenbin's question, which is more relevant.
Okay, Wenbin, do you want to ask your question?
Yeah, so I was very interested in the triples where you have the inner binary merged. So what's the prospect that the inner binary merger product somehow can merge with the tertiary?
Yeah, that's a good question. I think it depends a lot on the previous evolution. So the systems that we considered here, they don't undergo mass transfer. So that means that the inner orbit is pretty wide, and therefore the outer orbit needs to be even wider. So for these sources, I think that's not so likely. Not likely. For sources where the inner binary does undergo mass transfer, they can end up much more compact, right? So
yeah,
there I know your paper, right? So I think it's very interesting. But from my point of perspective, I really would like to simulate the evolution to really see how common that is, because we deal with systems that need to stay stable for this long.
Yes, me too, very much so. Yes.
So yeah, I think that's very interesting future work.
Yeah, especially for low metallicity. I mean, especially in the low metallicity cases that Rodriguez have simulated, I would like to know whether they can actually undergo second generation merger. Can I ask you one more question?
Yeah, of course. So for so with the Rodriguez paper, because he has a bunch of papers, right? If you're referring to the one from this channel, and in that channel, I don't expect sequential mergers.
Yeah.
Maybe. Can you put up your hand again so we can take Tony in between, because he had the question as well? Tony?
Sure. I just had a question of clarifying the hybrids. How much does this depend on mass transfer models versus, just a normal star will evolve into a hybrid in some sense. Where I assume there'll be some carbon and oxygen component and some helium component. But then you have specific scenarios where, now you have the hybrid's actually the more massive white dwarf, and the less massive white dwarf is a pure carbon oxygen. How much is this just putting together different things versus actually coming directly through the stellar evolution naturally?
So I want to make sure that I understand your question directly. Is it, or completely? So is the question, how different is this from other scenarios?
No, I guess are you just putting together different masses and all different combinations and seeing what you get? Or are you simulating it from first principles where the mass of the helium layer, for example, on top of your carbon oxygen white dwarf was self-consistently solved for through the
So it's
binary.
actually, the project consists of 4 different simulations. One is, the binary evolution. So that gives us an idea of how many sources with which mass combinations. Then we did detailed simulations of stellar evolution with MESA to see how big would that helium layer be on these stars that are being stripped, because that's something that, the binary population synthesis, right? That's something that binary population synthesis wouldn't be able to give an answer to. And then with those detailed models from MESA, we then put them into the hydro codes and simulated, well, Joseph did, and simulated the merger. So I would say it's a combination of these 4 codes that are all consistent within each other.
Good, thank you.
Yeah, and so of course, all white dwarfs have an atmosphere, right? Like, 60% of white dwarfs have a hydrogen atmosphere. So, but those layers are very thin. So the layers that I'm talking about here, they're really significantly different than, your typical white dwarf that we used to be thinking about.
Okay, Van, go ahead.
Oh, thanks. So I want to ask about the triple fraction. One of your plot, you're showing with little triple stars, showing the triple fraction. I never understood those Senna, their latest papers, because those fractions are pretty complicated. I mean, the papers are pretty complicated. I never grasped the following question, because they show that nearly 100% of the systems, individual systems that look at, they are either binary or higher order systems. So that's the first number. So it's nearly 100%. They are all in multiple systems. Whereas, as you're saying, 30% of them are triples. I wonder what's let's say if you already have a binary, what's the fraction of that having a third body? What's the fraction of those already in binary having a third body? Because let's say if I only care about LIGO sources, I only care about binaries anyway. So non-binaries, I don't care. So what is that fraction known?
Observation, well, so in the group of Yuksana, they didn't, so they're the observers, right? They have the best, and their collaborators, they have the best samples of massive stars, and therefore the best handle on if these stars are in binaries or in triples or in quadruples. But they haven't modeled yet the selection effects. So the 30% that I quoted is just from them having a direct look at their observations without taking selection effects into account and seeing how many are triples and how many are binaries. And then one thing to keep in mind is when you give the binary fraction, it's usually quoted as having at least one companion.
Yeah.
So also including triples and also including quadruples.
Yeah.
So I think the best work on this, where the selection effects have been taken into account, best way we know how, then is Max Moh's work, right? That shows for the OMB type stars. Let me phrase it accurately. So shows that about 80% of systems have 3 or more companions. So only 20%, yes, I think it was 75%, only 20% would be binaries, like really truly binaries and no
okay.
components.
Wow.
And like a few percent was single. So if you follow that, then triples and quadruples are 4 times more common.
They're everywhere.
Yes,
Oh,
exactly.
yeah.
But it's also we have to keep in mind that it's based on our understanding of selection effects. And that's all stuff. So
yeah. Thanks.
Okay, so I also wanted to ask a question, but apparently there is no raise hand feature when you're the host. So I wanted to ask, similar to Tony, about these hybrid white dwarfs. So the emerging double white dwarfs has been modeled with binary population synthesis previously. Also, you have done some work on this. How has the remnant been modeled before of a strict star, which has caused researchers then not to discover this type of merger? Is there some unreasonable assumptions that have been made, or how has this been done, Silvia?
I think until a few years ago, we simply didn't really track it very much. So in a way, it was always there in the codes, but you know, you find what you're looking for. And if you're not looking for something, you're not gonna find it. So then, you know, slowly that, you know, interest in that helium layer starts coming, and therefore also this interest in the hybrids. So for example, there's some work from Lev Jungelsson of a few years ago where he detailed which of these mergers would have a hybrid and which not. The other ingredient to take into account is that for a long time we were focusing on mergers that have a mass above the Chandrasekhar mass. So we were completely, you know, focused on massive white dwarfs. The problem is that there are not so many massive white dwarfs. So that was one of the reasons why it was so hard to get the observed rate, or to, you know, make a theoretical estimate of the rate that matches the observed rate. Now, the other thing that happened in recent years is that people realized that if you somehow blow up a lower mass white dwarf, a 0.8 solar mass white dwarf, it also looks like a type 1a. So we don't need to reach Chandrasekhar mass. The Chandrasekhar mass is not something that then, you know, is of importance to the supernova type 1a. We just need to somehow blow up a 0.8 solar mass white dwarf. And it's this double detonation that does that. So I think it's this, you know, research goes in steps, and I think it's this gradual step towards lower mass white dwarfs, and therefore reaching the mass regime where hybrids all of a sudden pop up. And when we were only focusing on the very massive white dwarfs, there's no hybrids. I don't know if you remember from the plot, but pretty much the helium layer vanished for masses above 0.7. So that just made it never relevant. So bit of historical fact, I think.
Yeah, thanks for helping out with that. Andy, you have a question.
Yes, I do. So I have questions about things that we know are, or think are mergers and or mass transfer objects. So one would be blue stragglers in clusters, and I was wondering how your triple idea would affect, whether you thought about that to explain a fraction of the blue stragglers and how the statistics compared. And then also barium stars or CH stars in the metropole halo, they're more field stars. They've all been shown to be doubles, so far as I know, and I don't know if there are any triples. And I was wondering whether you had any thoughts about statistics of those as well.
Yeah, I think that's I'll give two different answers. So for the triples in clusters, it depends which clusters you're talking about, because right, these triples tend to be much wider than binaries. So in globular clusters, they likely do not survive for a very long time. So I think there's work from Nathan Lee that showed that for open clusters, these triples could be interesting. So I think it, you know, and then for open clusters, this triple channel to make blue stragglers, that could be interesting. But if it can also explain the, you know, the other ones, it would be harder for the triple to survive that long. Then your other question is about carbon and metal poor stars, and is this about these sources that show some sign of previous interaction, but they tend to have orbits that are very wide, say 10 to the 3 days?
I'm talking about barium stars and CH stars in the halo, where they have S-process elements and sometimes carbon in their atmospheres that must have come from an AGB star companion. yet they're not in the AGB phase, they're more in the red giant phase. And then looking closely at them, they all seem to be binaries with white dwarf companions. And I don't know of any triples, there may be, but I was just wondering whether you would have expected a significant fraction of them, since I thought that you thought that there was enhanced mass transfer in the triple system.
Yeah.
So I was just wondering whether we should go out and look for triples amongst the barium stars, for example.
I think if the question, should we look for triples, then yes, always. In this particular case, yeah, these particular systems intrigue me very much because they have wide orbits and they're still eccentric. And because they, the enhancement in barium would, would indicate that maybe they have accreted that barium from their companion when that white dwarf was still an AGB star, right? But for me, the problem is, how can we explain their eccentricities? Because usually, in the way that we model these interactions, is that the mass transfer would lead to circularization of the orbit. And this problem is there for the barium stars, carbon hand metal bar stars, but also for post-AGB stars. It's also there for some SDB stars. And I think there's one more type of star. So for me, it's a problem that's even more larger than just the carbon hands metal bar stars. Now the question is, if we see it in so many systems, can triples then do it consistently enough? That's something that I'm not sure. It might be that this is so common that I'm kind of leaning to something that we might not understand in just the mass transfer phase. That because these are such wide systems, maybe something that we're modeling not correctly there that leads to this eccentricity. That's my hunch without doing research on it.
Okay, thank you.
Okay, so I think we need to wrap up. So let's thank Silvia again for this very interesting talk. And yeah, so thanks Silvia for also agreeing to give a talk so late in the evening. I think so there is a schedule that you have, and it would be good to go and double check so that there is all the links and everything that you need also for the people who will talk with Silvia. So please go double check, and otherwise, thanks again.
Thanks so much.
Thank you.